Friends, let us continue our discussion on thermodynamics and chemical reactions. And to recap what we saw in our last session, if we have a reaction of the kind, let us say summation nu j aj equal to 0, then the condition of equilibrium works out to be summation nu j mu j, where mu j is the chemical potential equal to 0, and from there we saw that we can define the equilibrium constant Ka as product of activity of species j raised to nu j and product over all species j. So, before we proceed further, let us take few examples and see how this information is useful. So, let us say that we have a reaction in which lactic acid reacts with ethanol to give ethyl lactate plus water. So, we have a reaction esterification of lactic acid, this is lactic acid, ethanol giving ethyl lactate and water. Ethyl lactate is one of the important component of making biodegradable polymers, and it has several other uses as well. The equilibrium constant Kc from thermodynamic considerations comes out to be 2.4. So, now we would like to find out how much of ethyl lactate can we get, and remember this is the maximum ethyl lactate that you can get, because you cannot go beyond equilibrium, equilibrium is the upper limit. So, to do this calculation, let us say that we started with 1 mole of ethyl 1 mole of lactic acid, 1 mole of ethyl alcohol or ethanol and 0 moles of ethyl lactate and water, and our extent of reaction is, let us say, alpha. So, at any given time 1 minus alpha is what lactic acid is remaining, 1 minus alpha is what ethanol is remaining, and alpha each of ethyl lactate and water is formed. So, let us label this species A1, A2, reaction is A3 plus A4. So, now we can define our equilibrium constant. Since note here that I have said our equilibrium constant with superscript or rather subscript C, which denotes I am working with concentrations, it is a liquid phase reaction. So, easy to work with concentrations. So, this we can define as product of C1 stoichiometric coefficient minus 1, C2 stoichiometric coefficient minus 1, C3 and C4, each with stoichiometric coefficient 1. This we can conveniently write as C3 C4 divided by C1 into C2. So, now let us put our compositions or concentrations of all these species. So, this is alpha into alpha divided by 1 minus alpha into 1 minus alpha, and as per our thermodynamics this is 2.4. I can now so this is my equilibrium value. So, there is only one unknown alpha and I can solve it and I get alpha equilibrium approximately 0.6. What this implies is that at equilibrium if we start with 1 mole of lactic acid, at best you can get 0.6 moles of ethyl lactate. Reaction cannot proceed beyond that, roughly 60% conversion. So, now that raises a question, should we just stop here, or are there any ways we can overcome this limitation? Indeed, there are ways, and as you can think in the following manner. For example, while this reaction is going on, suppose I remove this ethyl lactate by some means, let us say distillation. So, if I remove this ethyl lactate by some means, then what will happen? The reaction will go from lactic acid and ethanol to ethyl lactate, but ethyl lactate has been removed from the system. So, this reaction will continuously keep going from left hand side to right hand side, because equilibrium will not be reached now, because we are continuously removing this. Mathematically, what will happen is the following. Suppose that I say that I remove some quantity of ethyl lactate. So, what is beta is the quantity that I am continuously removing. So, now what we have to change in this equation is that our definition of equilibrium constant and the value is same, but this is now alpha minus beta into alpha. So, alpha minus beta into alpha divided by 1 minus alpha into 1 minus alpha, and this will be now 2.4. If beta is 0, we got our alpha equilibrium as 0.6, but for any non-zero value of beta, and of course, we are looking for positive values of beta, you can see that this equation will lead to a solution where now alpha E will be greater than 0.6, depending on what is this value of beta, or in other words, we are able to overcome the limitations of thermodynamics by combining reaction with distillation. So, we have reactive distillations and thereby overcoming this limitation. So, the point is that thermodynamics therefore tells us a whole lot about how we should operate our reactor. Let us go a little further, and these are some of last time we stopped here. This is basically the equation we just now used for calculating calculating the value of alpha, that is what equilibrium value we will get. Now, a close examination of this function reveals some interesting property. Although we will not go into the mathematical details of this, but you can believe me when I say that if remember our equation is Kp equal to f of alpha. So, that value of alpha which satisfies this equation is my equilibrium value. Now, it turns out that if you look at this function f of alpha versus alpha, it is always a monotonic function. That means, it is continuously increasing as alpha increases, and we are looking for solution alpha E such that f of alpha is equal to Kp. So, graphically I can put some value Kp. So, suppose this is my Kp value, then wherever Kp becomes f of alpha, that is this particular point, this is my alpha equilibrium. This leads to several interesting observations. Firstly, f of alpha is a non-linear function, but it is a monotonic function. So, there is a unique value of alpha. See, what is it is a monotonic function. What is a non-monotonic function? This is a non-monotonic function, it goes up and down. So, now if this was my for some reason if this was my alpha and if I had my Kp value over here, there are two possible solutions. However, real thermodynamic one can actually show it, this never occurs. So, this is the only possibility. There is another interesting observation which we will use to see some properties of equilibrium. If you look at this function, it is monotonic, which implies that the derivative of f of alpha with respect to alpha or f prime alpha is always positive. So, f prime alpha is always positive, that means the derivative of this function is always positive. Now, why is this interesting? Let us go back to our condition of equilibrium and re-examine this for, let us say, for this general reaction nu1 A1 plus nu2 A2 and so on equal to 0. We got our equilibrium constant Kp as a function of alpha, extent of reaction, and solution of this for a given condition, whatever is the value, is my value of alpha E. Now, let us examine this f of alpha. We see several things here. Let us start with nu j. These are the stoichiometric coefficients and there is nothing much we can do about it. Given reaction, these conditions are fixed. So, if we look at this function is dependent on alpha and we saw its behavior just few minutes back, but it also depends on pressure P. So, it is a function of pressure. It is also a function of how many moles of species that we start with. That is, in our lactic acid example, depending on whether I start with 1 mole of lactic acid or 2 moles of lactic acid, I will get different value of N J0, and so this is a function of N J0. And from our thermodynamic considerations, for a perfect gas mixture, assuming perfect gas mixture, Kp is a function of temperature. So, now examination of this equation allows us to look at what happens to the extent of reaction under different operating conditions. Under different operating conditions, what happens to the extent of reaction? If I know that, then I can decide what operating conditions should I be using. The choice is obvious, whatever that leads to increased value of extent of reaction is the condition we are looking for. So, how do we find out? Slight algebraic manipulation of this gives us, that is, we take derivative of this function with respect to any operating condition y. Okay. Y can be any operating condition, temperature, pressure, or even the moles and so on. Then we can take a derivative of f, and since f depends on operating, because operating conditions appear also in f. So, we can express it as del f del y, the partial, plus how f depends on alpha and how alpha depends on y. So, if we now take these two together, we get the following. For this reaction, how alpha changes with operating condition is given in the form of some constant c multiplied by f of alpha divided by f prime of alpha. Now, f prime is always positive, f is also positive. So, how alpha depends on a given operating condition, that is this derivative, its sign will be determined by sign of this constant c. And let us look at some of the operating conditions. For example, if our y is temperature T, then this constant C is delta H by RT square. What is delta H? Delta H is the heat of the reaction. So, C depends on the sign of C depends on sign of delta H, because R is a universal gas constant, T is the temperature, these are all positive. So, if delta H is positive, that means we are looking at endothermic reactions, then del d alpha dt is positive, or in other words alpha will increase as temperature increases if the reaction is endothermic. If del H or heat of reaction is negative, that means we are looking at exothermic reaction, then del alpha del T will be negative. That means alpha will decrease as the temperature is increased. So, we now know that endothermic reactions are favored, or the equilibrium constant or equilibrium extent of reaction is higher if temperature is higher, and for exothermic the reverse is true. What happens if we change pressure? Now, it turns out the constant C in this case is summation nu j of this stoichiometric coefficient. Now, what do we mean by that? Let's take this reaction of ethane formation. Okay. So, what do we have here? Let us say A1, A2, A3. So, what is summation nu j? That is addition of stoichiometric coefficient 1 plus 1 from the product side minus 1, that is plus 1. So, what is happening in this reaction? This reaction is accompanied by increase in number of moles, and that is reflected in summation nu j value, which is positive. So, if nu j summation nu j is positive, that means there is increase in number of mole, then what will happen to our d alpha dp? That will be negative, or in other words, for cracking of ethane, as we increase pressure, the equilibrium extent of reaction decreases. So, this now explains why pressure should be low for this reaction, because if you have high pressures, then the extent of reaction or equilibrium is adversely affected, because there is increase in number of moles. If there is a decrease in number of moles, what can you expect now? The converse, that if the reaction is accompanied by decrease in number of moles, that means this summation nu j is this one over here is negative, then C will be positive, or in other words, in that reaction d alpha dp will be positive. So, those reactions in which there is a decrease in number of moles, we have to carry them at high pressures. If there is an increase in number of moles, we have to carry it at low pressures. Now, tell me what should happen with this kind of reaction. Ammonia synthesis, 2 minus 3 minus 1, again summation nu j, 2 minus 3 minus 1. So, minus 2, that means there is a decrease in number of moles. So, ammonia synthesis has to take place, it is a high pressure reaction. This is a low pressure reaction. This is how the operating conditions are determined. Same thing for temperature, we will come look at temperature once again, but let me just leave it for you to figure it out. What happens if there are inerts in the system? Now, how does inerts affect the equilibrium? Recall that f of alpha has NT0, NT0 has inerts in it. So, if we change inerts, NT0 will change, therefore, alpha will change. I'll leave it for you to work it out, that what happens if you increase the inerts. Let me give you an hint. In this reaction, we add steam as inerts. I think you should be able to take it forward from there. Let me just complete the discussion by looking at what happens to equilibrium conversion or extent of reaction for exothermic reaction. We just now said few minutes back that as temperature is increased, for exothermic reactions, the extent of reaction decreases. So, at lower temperature our extent of reaction is high, at higher temperatures the extent of reaction is low. This raises several interesting questions. For example, let us say that we carry out a reaction in an isothermal manner. Now, if we carry out reaction in an isothermal manner, let us say this particular temperature, then we can get this value of our equilibrium extent of reaction, roughly let us say whatever numbers do not matter, but qualitatively this is my extent of reaction if I do isothermal process. Now, if I do a process, adiabatic process, from thermodynamics you would have learned what is an adiabatic process, where there is no heat added or removed from the system. And remember that we are looking at an exothermic reaction. So, if we have an exothermic reaction and we do not add or remove any heat, there will be a natural tendency for temperatures to go up as reaction proceeds. Now, we can show that pictorially on this equilibrium conversion or conversion versus temperature diagram by following a trajectory of adiabatic reaction, and this is what conversion that we can expect. Because temperatures are increasing, the equilibrium conversion compared to an isothermal process will be lower in an adiabatic process. Now, why is this interesting? This is interesting because look at it this way. For a reaction or for a reaction to progress satisfactorily, there are now two constraints on us. One, we should carry out reaction as fast as possible, and we should also worry that reactions are reversible. So, there is a constraint on how much maximum conversion you can get, which thermodynamics has put on us. So, exothermic reaction, lower temperatures, higher the equilibrium conversion, but lower temperatures also means lower rates. So, if even though conversion is very high, the time required to reach that conversion will be low, and we will discuss that as we proceed. But I just want to introduce this concept at this point. On the other hand, for adiabatic process, temperatures are higher. So, reaction rates will be faster, but equilibrium conversion will be low. So, that is a dilemma that we somehow have to resolve. Endothermic reactions, the equilibrium conversion increases as temperature increases, and this is what we see. As we are increasing the temperature, the equilibrium conversion is increasing. Y axis is our equilibrium conversion. So, if we are doing reaction at let us say this particular temperature, we can get in an isothermal process this conversion, whereas for an adiabatic process we can get only this much conversion. So, for endothermic reactions, what happens in an adiabatic process? Because there is a absorption of heat, the temperatures naturally tend to decrease if we do not add or remove anything, that means adiabatic operation. So, we have not only we have lower temperatures. Lower temperatures means lower rates of reaction, but in this particular case it also means lower equilibrium extent of reaction or conversion, a situation which is completely unfavorable. So, higher temperatures, higher rates, higher conversions. But story does not end here, as we will see when we design non-isothermal reaction. You have an endothermic reaction, you want high temperatures, naturally the system has tendency to absorb heat. That means, you will have to continuously keep on supplying energy to maintain those high temperatures. Again a dilemma when it comes to design of reactors. Now, let us just extend this argument for multiple reactions. So, suppose we have more than one reaction. For example, that example of carbon monoxide, carbon dioxide and so on. So, if you have R reactions, let us say summation nu ij aj equal to 0, then we can write for each of those R reactions corresponding equilibrium constant Kpi. Now, it turns out that when the system is at equilibrium, all reactions individually are at equilibrium. So, let us say that we have these reaction. So, let us take an example. Let us say that CO plus 2H2 gives rise to methanol. Okay, that was one of the reactions, and we also had another reaction, let us say H2O. So, now we have two reactions. Now, for multiple reactions, it turns out that each of these reaction is at equilibrium. So, as before we had defined nu 1 j as stoichiometric coefficient of all the species for this particular reaction, nu 2 j as stoichiometric coefficients of all species for this particular reaction. So, we can write equilibrium condition as follows. Let us define this species as 1, 2, 3, 4 and let us say this is the fifth one. So, what is my first reaction? My first reaction is A3 minus A1 minus 2A2 equal to 0. What is my second reaction? This is my species 2 and this is my species 1. So, A1 plus A5 minus A4 minus A2 equal to 0 is my two reactions, and remember we are talking only independent reactions. So, these are, if we add them and create a third reaction, that is not going to count. So, if this reaction is at equilibrium, then the equilibrium condition is summation nu I j mu j equal to 0 for all these reactions I going from 1, 2 up to R. Okay. So, let us try to write down the equilibrium condition for first reaction. So, that one will be 1 into mu 3 minus mu 1 minus 2 mu 2 equal to 0. I am just picking up corresponding stoichiometric coefficients, and the second one would be mu 1 plus mu 5 minus mu 4 minus mu 2 equal to 0. So, I have two conditions. I can use the same logic as before, express these chemical potentials in terms of operating conditions and partial pressures. If, for example, if we assume perfect gas law, both these conditions individually. So, for this condition, for example, I will have equilibrium constant Kp1 for this reaction, Kp2 for this reaction. So, we have our equilibrium constant Kp's and Kp1, Kp2, then again come to mole balance. Now, what I do is I define extent of reaction alpha 1 for first reaction, alpha 2 for second reaction. So, my unknowns are alpha 1 and alpha 2, but I have two equations Kp 1 and Kp 2. So, I can find alpha 1 and alpha 2 value, that is how far this reaction will go, how far this reaction will go, that is these two separate reactions when we reach equilibrium. So, this is how we extend the thermodynamic considerations to multiple reactions, which incidentally will be the most general case to consider. Before we close our discussion on thermodynamics and chemical reactions, this you have seen before, but just a recap of how do we calculate the heat of reaction. We talked about heat of reaction either positive, that means an endothermic reaction, or negative as an exothermic reaction. Incidentally, steam cracking is an endothermic reaction, ammonia synthesis is an exothermic reaction. So, now you can consider what temperatures other conditions should be, but how do we calculate this heat of reaction? This is simply done based on again going back to our reaction and calculating the heat of reaction delta HR as summation nu j Hj, where Hj is the partial molar enthalpy of the species J. So, if this is a reaction, for this reaction it will be simply mu 1 H1 plus nu 2 H2 plus nu 3 H3 plus nu 4 H4, it will be my heat of reaction. Now, what is partial molar enthalpy? If you recall definition of specific heat, Cp del H J del T. So, partial molar enthalpy is a function of temperature, which we can relate to reference condition Hj0 plus integral from reference conditions typically 298 to any temperature Cpj dt. Cpj is the specific heat, which again is a function of temperature. So, if you now take this equation and put it back into this, we can combine the reference conditions together as a summation series of nu j Hj0 and this integral as summation nu j integral Cpj dt, and then we get heat of reaction at any temperature is the reference condition heat of reaction plus summation nu j integral 298 between the limits 298 and temperature T Cpj dt. So, this gives me the idea about how heat of reaction is computed. In many calculations, if you want to do a quick estimate of what is happening, you can actually look at reference condition heat of reaction to see whether reaction is exothermic or endothermic. It is true that there will be some contribution from this particular function, the second part, but suppose we make an assumption, and engineering is all about making assumptions, but right kind of assumptions, and it is a reasonable assumption at least in many cases that Cp is a constant, it is not a function of temperature. Then this reference condition and the actual temperature heat of reactions are not very far from each other. It is true, numerically they will be different, but it is not significantly different. So, with this we now close our discussion on thermodynamics and chemical reactions. But before we conclude, just few keywords that we came across in this particular session. Firstly, thermodynamics is about finding out the equilibrium conditions and how those conditions are influenced by various operating conditions, that is as far as the reaction engineering is concerned. So, what we would like to know is, for example, given temperature and pressure, what is the maximum conversion I can get in my reaction, and then ask the follow up question, what happens if I change temperature, what happens if I change pressure. So, in order to answer this question, what did we do? We went in a systematic manner, that is starting with Gibbs equation for free energy change. We got a condition of equilibrium. That condition of equilibrium involved chemical potential. We got some models which will relate chemical potentials to the operating conditions, including temperature, pressure and composition, and then using the this equilibrium condition and the model for chemical potential, we calculated what will be the equilibrium extent of reaction or equilibrium conversion. We then also saw how this equilibrium conversion will be influenced by operating condition. For example, in case of operating conditions being temperature, it depends upon the heat of reaction, whether it is positive, that is endothermic reaction, the temperature increase will lead to increase in conversion. If heat of reaction is negative, that means an exothermic reaction, the increase in temperature will lead to decrease in conversion. We can also find out what happens to pressure. For example, increase in number of moles favored by decrease in pressure and vice versa. Incidentally, you probably have done this for quite some time, right from your high school days probably, Leach-Atelier's principle, but we saw more formal part of it. So, with this we will conclude our discussion on thermodynamics, and now let us move into the next topic, namely the rates of reaction or the kinetic aspect of reactions, and this is of course is what will be of concern to us when we talk about reactor design and so on. So, let us continue our review of undergraduate material, and let us talk about today about the kinetics. So, when it comes to kinetics, what are the basic ideas or basic concepts? What we are going to just review quickly over here is kinetics of different types of reactions, a power law kinetics which is quite often used, law of mass action kinetics which is a specialized case of power law kinetics, and we will also see few simple rates of few simple reactions. Before we go into rates of reactions, we will just briefly go over various different ways in which reactions are classified. Reactions are classified based on three different things, starting with, let us say, mechanism of the reaction, that is whether the reaction is elementary or non-elementary. For example, if you consider this chlorination of nitric oxide to give nitrosyl chloride, this reaction is an elementary reaction. We call a reaction as elementary reaction if the reaction takes place the way it is actually written down. For example, here the formation of 2 moles of nitrosyl chloride is a result of direct single step interaction of 2 molecules of nitric oxide and 1 molecule of chlorine, just single step interaction, and hence we call this reaction as elementary reaction. Of course, very few reactions of commercial importance are elementary, they are all non-elementary. That means, these are not single step reactions, but there are several steps proceed from a reactant side to product side. But for an elementary reaction, for example, in this example, the molecularity of the reaction is 2 plus 1, 2 from nitric oxide, 1 from chlorine, so 3. So, this is an example of termolecular reaction. Similarly, there are several examples of unimolecular reactions, bimolecular reactions, that is molecularity 1 unimolecular, molecularity 2 bimolecular, unimolarity 3 termolecular. Thing to remember is there are no known reactions of molecularity higher than 4, that is elementary reactions. So, moment you see the molecularity of a reaction is 4, one can strictly say, or one can immediately come to a conclusion, reasonable conclusion, that this cannot be an elementary reaction. Okay. Reactions are also classified based on direction of reaction. Strictly speaking, no reaction is irreversible, all reactions are reversible, but thermodynamic considerations tells us for all practical purposes, some reactions such as cyclopropane to propylene always proceed from left hand side to right hand side. That is almost 100% conversion of cyclopropane to propylene. So, essentially irreversible reaction. But a reaction like transbutylene to cisbutylene is an reversible reaction. This arrow is missing, but take it from me, it is going from left hand side to right hand side and right hand side to left hand side, something we talked about in our equilibrium and thermodynamics. So, this is reversible and irreversible reactions. And then we can also classify reactions based on how many phases are present in the system, that is whether it is a homogeneous or heterogeneous reaction. For example, take this cracking of ethane. Ethane, which is in the gas phase, gives rise to ethylene, which is also a gas, and hydrogen, which is also a gas, and in the reactor there are no other phases except gaseous phases, and hence we call this reaction as homogeneous reaction. On the other hand, the reaction of absorption of carbon dioxide into alkali, into hot alkali, in fact, this is one of the ways of getting rid of carbon dioxide from the gaseous emissions coming out of the reactor. This reaction, to give bicarbonate, this reaction is a heterogeneous reaction, because one of the reactant CO2 is in the gas phase, another reactant NaOH in the liquid phase, the product is also in the liquid phase. So, more than one phase, and there are all kinds of catalytic reactions, for example, where both gas reactant and product can be in the same phase, but reaction does not occur if unless there is a catalyst, that is in the phase separate from the reaction phase. So, we also call these reactions as heterogeneous reactions. To begin with, we will focus on homogeneous reactions and make suitable modifications as we proceed. So, just few terminology to set the background for different kinds of reactions. For example, we first start as usual with single reaction. Let us say that we have a reaction summation nu j aj equal to 0 taking place in a closed isothermal constant pressure system. Then we define the rate of reaction R as rate of change of extent of reaction alpha with time d alpha dt normalized by the volume of the reacting mixture. I will repeat again, for an closed isothermal constant pressure system, and this is important to realize. Later on we will talk about reactions in the open systems such as continuous stirred tank reactors. For that, we have a definition of a rate of reaction which is slightly different, but for closed isothermal constant pressure system, the rate of reaction is given as rate of change of extent of reaction d alpha dt normalized by the volume of the reacting mixture. We saw earlier that alpha is an extensive property, has a units of moles, let us say. Okay. So, alpha is units of moles, time let us say is in units of minute, and the volume of the reacting mixture let us say in decimeter cube, and hence rate is in the units of moles per dm cube per minute. You could use different units for mass, time and volume, but what is important is presence of all these three quantities in the expression. So, rate is always in moles per minute per dm cube. Now, I mentioned few minutes back about heterogeneous reactions and homogeneous reactions. Now, if a reaction is heterogeneous or rather homogeneous, then this V that we are talking about is the volume of the reacting mixture, not the reactor. There is a distinction to be made here. For example, if you have a reactor and there is a liquid phase reaction and this is only 70% filled, then this volume we are talking about is the volume of this reactor, the volume of this reacting mixture and not the volume of the entire reactor. These two are different things. But for example, later on we will also see that when it comes to the heterogeneous reactions, we sometimes define rate in terms of extent d alpha dt per unit normalized by weight of the catalyst. These are in fact used for catalytic reactions. So, in this case the rate is expressed in terms of moles per minute per gram of catalyst. So, for catalytic reactions we have this particular definition. Now, we have this extent of reaction d alpha dt, and how did we define alpha? We had defined alpha based on Nj is Nj0 plus nu j into alpha, or alpha is Nj minus Nj0 divided by nu j. So, if you substitute for alpha in this particular expression, then we will get R equal to 1 over V 1 over nu j d Nj dt d alpha dt as 1 over Nj, which we can write 1 over V d Nj dt as Rj, okay, and write R equal to Rj by nu j. What is the difference between R and Rj? Unit wise they are same, but Rj is the rate of change of species J and R is the rate of the reaction of this particular reaction. So, Rj is for the species, R is for the reaction, and these of course are related, that is Rj by nu j is equal to R. Few things before we stop for the day. Alpha, remember, is always starts with 0 and is always positive. So, d alpha dt is always positive, or in other words R is always positive, at best it can be 0, but it is always a positive quantity. So, R is always positive, but nu j can be positive or negative depending upon the stoichiometric, whether it is a reactant or product. So, if we have R equal to R j by nu j, this is always positive. This, if j is reactant, nu j is negative, that means R j is negative. That is, for a reactant the rate of change is negative or reactant gets consumed. For product it gets formed, it is always positive. So, these are all related to each other. So, we will stop here, and in the next session we will look at what are different ways in which we define the rate of reaction, how does it depend on the operating conditions, and then how we use this information in design of reactors. That will be in the subsequent lectures. Thank you.